Well, here we are, right where I left off at the end of the last recording. The topic this time is something that's going around in a circle, that would be the circular part of it, at a constant speed, that would be the uniform part of it. So imagine yourself in a car on a perfectly circular track with the cruise control turned on. And you're just going around and around at 50 miles an hour, and you're going to do that like until you run out of gas, which sounds completely pointless, but actually, if you're just driving down a regular road and you come to a curve, for the few seconds that you're on that curve, you're in exactly the same situation I was just talking about. It's just you don't keep doing it indefinitely after that. But while you're on the curve, you might as well, it's the same thing. This is a type of motion that comes up in several situations. When we get into physics 132, we'll refer back to some of this stuff, because if you have a charged particle like an electron moving perpendicular to a magnetic field, it shoots around in a little circle at a constant speed. In physics 3, when you get into atomic physics, if you have an electron orbiting like in the Bohr model of the atom, it's a little miniature version of the moon orbiting around the Earth, basically. Uniform circular motion. Of course, the moon's orbit is not a perfect circle, a little bit of an approximation going on there, but approximations are often useful things because they simplify things. So although you are driving, you got the cruise control turned on, what did I say, 50 miles an hour? I don't remember if I said 50 or 60. Well, now it's 50 anyhow. So you've got the cruise control set for 50 miles an hour, and the needle stays right in front of the 50, but you are accelerating. This may seem like a bit of a paradox, because acceleration, by definition, means the rate at which your velocity is changing. And didn't I just get done saying that your velocity is not changing, that it stays 50 miles an hour? No, I did not say your velocity is constant. I said your speed is constant. Velocity is a vector, and it has a direction, and the direction is changing, and the details look like this. So yeah, this is the course where I go in and do things right, which in this case means you have to sit there and listen to me explain why you should believe. In a more simplified course, I just write down the equation, say, here it is, trust me, but that's bad science. I am going to justify everything to you, and justification goes like this. So there's the circular path that this car I was talking about is following. And this was supposed to be the center of the circle, but actually I think maybe the center is more like there. Well, it's just a sketch anyhow. So you're driving around in a circle in a car, and somebody's watching you from a helicopter, looking down from above. This is the path you're following. And originally, when this person in the helicopter who's watching you first looks down at you, your car is right there. The center of the circle is a convenient point to use for the origin. So R for radius. This original radius vector, R1, that's your initial position. And at that time, your car has a velocity v1. A short time later, your car is located here. And now, I have tried to draw both of these arrows the same length. That one may have come out a little on the short side. I don't know, I'd have to get a ruler, maybe that's a little better, but 50 miles an hour, 50 miles an hour. Both velocity vectors have the same magnitude. But at any given moment, the direction that your car is moving would be along a tangent to this circular path. I've drawn the vector a little bit off to the side just because that's where there was some empty space to draw it in. So I didn't have too many things on top of each other in my picture, but really it belongs right here on your car. And when your car is here, it's going that way. And when your car is here, it's going that way. So the car's net displacement as it goes from point number 1 to point number 2 is delta R. And I already explained, was that in section 3 or section 2? When in doubt, be vague. I've already explained recently how the delta R is, made a mess out of everybody's notes there. Delta R is R2 minus R1. If you reverse R1, okay, you take this one and put the arrowhead over here instead, that's negative R1. Negative R1 added to R2 head to tail would have this vector as the resultant. So that's delta R, R2 minus R1. An arrow pointing from where you were in the beginning to where you were in the end. Let's do something similar with the velocity vectors. Remember, vectors have this property called parallel displacement, which means that I can slide them around the page to any place I find convenient, as long as I keep them parallel to the original direction. So I've got some space to draw over here. Let's take delta, or let's take V1 and kind of go over there like that. And that may have come out a little longer than it was before, and maybe a little steeper, but that's what happens when you just make freehand sketches of things. Same thing with delta V2, parallel displacement. We're just gonna do that. So just as delta R points from the tip of R1 to the tip of R2, delta V points from the tip of V1 to V2. And incidentally, maybe I'll, looks like there's space to squeeze it in there. Initial and final velocity have the same magnitude. They're both 50 miles an hour. And so if I'm only talking about the speed, I do not need a subscript because speed never changes. The final velocity is different from the initial velocity because of the different direction, but speed is the same, just plain V. These are triangle with all the R's on it and the triangle with all the V's on it. Yeah, I didn't draw them very carefully, so maybe they don't look that way, but these are similar triangles, okay? If, you know, as you go from there to there, if the radius vector sweeps through, I don't know, 4 degrees, just to make up a number, well, the velocity is along a tangent. A tangent is always perpendicular to a radius. That's one of those theorems from geometry. So if the radius vector sweeps through 4 degrees, the velocity vector has to also turn 4 degrees in order to stay perpendicular to the radius. So that angle is the same as that angle. Furthermore, these are both isosceles triangles. The radius of the circle doesn't change as the car moves. And I just got done saying that the magnitude of the velocity doesn't change. So this side equals that side, this side equals that side. You've got 2 isosceles triangles with a similar, I guess you call it the apex angle. Geometry class was a while ago. Anyhow, that is enough to prove that they're similar triangles. And the reason that I care that they are similar triangles is because similar triangles have proportional sides. And that gives me an equation. Of course, physicists find equations exciting. The ratio of the short side to one of the long sides in this triangle is the same as the ratio of the short side to one of the long sides in that triangle. Now, along with that, distance equals speed times time. Back in section 1, it was delta x equals v average times delta t. The speed doesn't change anyhow. The reason this is approximately equals is because if you wanna get into the details here, delta r, the length of this arrow, that's the straight line distance from this point to that one. Whereas v delta t, the speed times the time, that gives you the distance along that circular arc from here to here, and that is slightly longer, okay? But as long as this angle is small, the straight line distance is pretty close to the curve distance. And in another couple of minutes, I'm going to take the limit where delta t approaches 0. And so if point number 2 approaches being the same place as point number 1, any difference between the straight line distance and the circular arc vanishes. But at the moment, we're thinking that, you know, this is just a couple of degrees, so these are pretty close to each other. Let's put these things together. So v delta t, well, wait a second. Technically, because my substitution is only approximately true, this would be approximately equals. So I put v delta t in here where the delta r used to be. Rearrange a little bit. I'm going to divide both sides by delta t, and I am going to multiply both sides by v to combine these two v's into a v squared. So then you take the limit where delta t approaches 0. As delta t approaches 0, this to the right of the approximately equals becomes the acceleration. And as delta t approaches 0, approximately equals will become equals. In the limit, approximately equals becomes equals, and delta v over delta t becomes a, the acceleration. So the real physics is understanding why things are true. Applications are for engineers. So this is why something moving along a circular path is accelerating at a rate equal to v squared over r, even though its speed is constant. You're keeping a constant, perhaps 50 miles an hour. You are accelerating because of the changing direction of the velocity vector. Called the centripetal acceleration for reasons that I'll get to in moments. The magnitude, of course, acceleration is a vector. It's got magnitude and direction. The magnitude of the acceleration as I just showed you, is equal to v squared over r. As for the direction, here's your circular path again. And if you slide v1 and v2 around a little bit so that they're, well, like this diagram that this picture that I drew back over here. Okay, let's just put it, you know, where the car actually is on the car's path here. Notice that delta V is across the direction of motion, pointing toward the center of the curve. Acceleration is, well, it's actually the limit as delta t approaches 0. I'm being a little sloppy with my notation here, but the point is you've got this vector, delta v, and you're going to divide it by the time. Time is a scalar, okay? Dividing by a scalar has no effect on a vector's direction. It just makes the arrow get longer or shorter if you divide by a scalar, or if you multiply by a scalar. So delta v and the acceleration have the same direction. People can be kind of bothered by this. It's like, well, if you're moving toward the north, how can your acceleration be toward the west? Well, the direction of your acceleration. Velocity and acceleration are two independent things, okay? The direction of the acceleration is not necessarily the direction of your velocity. The direction of the acceleration is the direction of the change. Delta V, divide by a scalar, no change in the direction. So the direction of the acceleration as shown on this diagram is toward the center. Direction is toward the center, which is what the word centripetal means, actually, okay? Translated into English, this means the acceleration toward the center. It's just, you sound smarter if you say something in Latin instead of English, but that's what it is. V squared over R is the acceleration toward the center. So magnitude and direction of something following a circular path. So that gets us down to here, where it says centripetal acceleration. And then it says centripetal force. Getting little chalky fingerprints all over the camera, but I guess that won't hurt anything. Remember Newton's second law? That was the one that said the summation of the forces acting on a body is equal to its mass times its acceleration. Well, in this particular situation, I just got done showing that the acceleration is equal to V squared over R. So if you put these two things together, maybe I should have, I don't know what this is like that. Summation of the forces is equal to mv squared over R. That is the force acting toward the center, okay? If you're on a curve, there has to be a force across the direction of motion to make you follow the curve. Newton's first law says that in the absence of any force, your car is going to go straight. This is a very bad thing when the road curves, okay? If there's been an ice storm and for some reason the sanders aren't out yet, so there's this sheet of very slippery ice all over the road, come along to the curve, the road turns left, you go straight, that's how you end up in the ditch. You obey the first law while the road underneath you curves off to the left. If you want your car to go to the left, there has to be a force toward the left, which would be toward the center of the curve, okay? So what this says is that force, which is not necessarily a single force, it's just the resultant of all the forces on your car, that net force has to equal mv squared over R for you to follow a circular arc. If the force is stronger than that, you would head toward the inside. You know, you would, I don't know where a stronger force would come from, unless you're intentionally steering in that direction. But if there was a stronger force than this, you will move closer to the center. You'll cross through the other lane and end up in the other ditch. And if the force is weaker than this, you'll move outward away from the center of the curve and end up in the ditch on your side of the road. Okay? If you're going to follow a circular path and not spiral inward or spiral outward, if you're going to follow a circular path, the net force on you has to be equal to this. Incidentally, I meant to say this a minute or two ago. Another argument for the idea that your car is accelerating toward the center of the curve. Okay? I mean, all this mathy stuff is all well and good, but if you don't like that, how about a physical argument? Loose objects in a car act as acceleration detectors. If the car accelerates forward suddenly, all the loose objects go flying toward the back. Or if the driver suddenly steps hard on the brakes, which gives you a negative acceleration, all of the loose objects in the car come flying toward the front, right? So now think about what happened. Whichever way your car is accelerating, all the loose objects appear to go the other way relative to the car, because what's actually happening is they're obeying Newton's first law while the car around them does not. If the car pulls abruptly away from a stop sign, loose objects are objects at rest remaining at rest. The car around them is not, and so the loose objects get left behind. They're exhibiting their inertia. Anyhow, if you go around a sharp curve faster than is really a good idea, loose objects are thrown toward the outside, thrown across the car toward the outside of the curve, right? And that's the same thing again. They're acting as acceleration detectors. The fact that you see them thrown toward the outside of the car shows you that the car is accelerating toward the inside of the curve, toward the center. Just like accelerating forward makes them go back, accelerating toward the center makes them thrown outward. So that's demonstrating it with experience instead of a bunch of geometry and algebra. Looks like we're down to examples. Time for another book. Number 4. Anybody, I mean, I think they bank the curves even on dirt roads. There aren't that many dirt roads left around here, so I'm not completely sure of that. But a perfectly flat piece of pavement with no banking and no crown in the middle to make the rain run off, that's a really poor way to build a road. But it makes the problem simpler if it's an exercise in a physics class. So let's say you're driving along a road and this road is a perfectly horizontal piece of pavement. So what's the fastest you would be able to drive around there if the pavement is wet? And where did I leave off? In the middle, I guess. Doesn't really matter. But we'll aim it right about there. First thing to realize, friction is what's providing the centripetal force, okay? Don't get the idea that centripetal force is something that occurs because you're following a curve. It's the other way around. You are following a curve because something exerts a centripetal force on you. With the moon orbiting around the Earth, the centripetal force is provided by gravity. If the Earth had a great big switch on the side, you could turn off gravity. The moon would immediately, here is the moon's former orbit. There's the Earth in the middle. If you threw the switch and turned off its gravity, the instant that the centripetal force went away, the moon would begin to obey Newton's first law. It would begin to follow a straight line and leave the Earth along a tangent to its former orbit. Okay? With an electron orbiting in an atom, it's the electrical attraction to the nucleus. Nucleus is positive, electron is negative, so there's an attractive force, again, kind of similar to gravity. In the lab for this part of the course, one of the simpler pieces of equipment that we have in any of the experiments, you're going to have a rubber stopper tied to the end of a piece of string, and you spin it around in a circle over your head. And in that case, the centripetal force is provided by the tension in the string. If the string was to suddenly break, the rubber stopper would move away along, well, I mean, would curve toward the ground because of gravity, but if you were looking down from above, you'd see it moving away along a straight line, tangent to its former path. So for a car on a curve, what provides the centripetal force? It's the friction between the tires and the road. Like I was saying a minute ago, if there was a sheet of ice that took away most of the friction, that takes away most of the centripetal force, and to some sort of approximation at least, your car will follow a straight line, which leads it into the ditch. So for this car in problem number 4, the centripetal force is furnished by friction. What may be less than obvious is we're talking about static friction. Static friction provides the centripetal force. Now you're saying, wait a minute, the car is moving. So when something's moving, isn't that kinetic friction? Well, almost all of the car is moving, but the bottoms of the tires are not, okay? Kinetic friction means sliding friction. And under normal driving conditions, anyhow, you don't get any of this kind of thing between the tires and the pavement. A given patch of rubber comes, as the wheel rotates, a given patch of rubber comes down, gets set on the highway, and then as the wheel continues to turn, it gets lifted off again. The only time you get any of this sort of thing is if you're driving like James Bond. But normally, there is no sliding, it's static friction between the tires and the road. Since the force of friction provides the centripetal force, that means, yep, it's still in view, it's the force of friction. Being the only horizontal force, I mean, there are other forces on the car, but they're vertical. The only force in the x direction is the force of friction, and so that equal mv squared over r. As I described, I think it was last week, the way static friction works is it provides however much force is needed to prevent slippage. So if you drive around this curve at 1 mile an hour, talk about a timid driver, you'll have a few newtons for the friction force. If you drive around the curve at 2 miles an hour, you'll have a friction force that's 4 times as much as what you would have had at 1 mile an hour. At 3 miles an hour, you'll have a friction force that's 9 times as much as you would have had at 1 mile an hour, and so on and so on. The faster you go, the bigger the friction force required to keep you moving along your circular path and not slide. Well, static friction can do this up to a certain point. There is a certain maximum force that friction is capable of providing. And if an even larger force than that is required to prevent slippage, you'll get slippage. So the maximum, how did I phrase the question? Fastest, yeah, without skidding, okay? Without skidding means the tires are not sliding across the pavement. And the maximum speed where you can do that is where friction would be at its maximum value. So that implies that F max is equal to the mass times V max. The maximum speed that you ought to be driving on this curve over R. Now, friction force the maximum force of static friction, as we saw a week ago, is the coefficient of static friction times the normal force. The normal force in this case is equal to the weight of the car. Doesn't have to be. We had some examples in section 3 where the normal force was not equal to the weight, like on an inclined plane, it was W times the cosine of theta. But in this case, it's just a level road. Here's the car. Friction force pointing toward the center of the curve. This would be like looking at the car from behind. You're in the next car behind this one, looking at it. You've got the normal force pushing up. So sum of the forces in the y direction is equal to 0, therefore n has to equal mg. They have to balance each other to maintain equilibrium. So F is equal to mu times N, and N is equal to the weight of the car. Kind of putting all that together. Divide both sides by m. Gone. M over m equals 1, m over m equals 1. The mass of the car is irrelevant, which, you know, that ties in with everyday experience. You're driving down the road, you come to one of those yellow signs by a curve. It doesn't say big heavy cars can drive 50 miles an hour, but little lightweight cars have to be 40. It just gives a certain safe speed for the curve. I've had people ask, well, you know, you can take the curve faster in a Corvette than you can in some box truck or something like that. Well, that's because the Corvette has a much lower center of gravity, and therefore it's much harder to make it tip over, okay? There are stability issues involved here. But as far as just simply do the tires slip across the pavement, then that is not significantly influenced by the mass of the vehicle. So Vmax is the thing that's being asked for here. So we want to solve it for Vmax. Multiply both sides by R. Take the square root, and you're going to have doesn't matter what order I write things in, I suppose. Like that. It doesn't really matter when you're working through a problem if you put the numbers in first and then do the algebra, or if you do the algebra first and then put the numbers in. I have a tendency to wait until the last minute to put the numbers in, because sometimes things like, sometimes things like this happen. If you try to put the numbers in first, you're going to be like, oh my gosh, I don't know what to use for the mass. They didn't tell me the mass. It doesn't matter, the mass drops out. Even if the question did tell you the mass of the car, it's irrelevant information. So sometimes things kind of simplify out like that if you wait to put the numbers in, but it doesn't really matter. So let's put the numbers in. For the coefficient of friction, you go to that table of friction coefficients. It's on one of the later pages of your formula sheet handout. There is an entry in there for rubber on wet concrete. Well, the question doesn't really say whether it's concrete or asphalt that this car is driving on, but since if it's asphalt, we don't have any way to finish the problem, I guess we'd better assume it's concrete. I sort of doubt there's a huge difference between the two anyhow. So that's where the 0.7 comes from. Rubber on wet concrete from the table in the handout. G is 9.8. If you still have to look that one up, now you probably won't for much longer. Somewhere around the 10,000th time you use something, it tends to stick in your memory. And the radius of the curve was given in the question, 30 meters. So you multiply the three things together, and it's about 14 meters per second, better known as 32 miles per hour. So they would probably post a curve for something like 20 or 25 miles an hour because, you know, you want to have a little bit of a margin for error. What's next? Skateboarder. So somebody is just going across the bottom in like a half pipe here. At this particular moment, they're moving at 10 meters per second. The circular path being followed has 5 meters for the radius. This person has a mass of 70 kilograms. The question is, what is the upward force? The normal force, the upward force on this person's feet. I'll start out by telling you how to do it wrong. The way you do it wrong is you get the formula mv squared over r. You put into it this mass, this speed, and this radius. You punch it up, put a little box around it, write the word answer next to it. No, sorry, gotcha. The right way to do it would be like this. Oh, I guess I've still got some space over here. Not that you can't just pause the recording anytime you want to, but I'm sort of in the habit of working in front of a live audience, and I like to leave things on the blackboard for a while, so anybody who's a couple of seconds behind me has a chance to write things down before I erase it. When I was slightly younger than I am now, I was going to the University of Rochester. One thing I noticed is when I got to the end of a course, somehow my notes were almost exactly the same length. It's like every course I took, I had almost the same number of pages of notes when I got to the end of the course, because that's how fast I could write. Well, I try not to leave people entirely in the dust like that. Anyhow, number 5. Here's the skateboarder. And we have a person on the skateboarder who in this particular rendition seems to resemble a refrigerator. But as I've said before, it's a good thing I didn't try to major in art. And artistic ability is not really necessary for this course. So, 2 forces acting on this person. The weight pulling down. 70 for the mass, 70 kilograms. 9.8 for the acceleration due to gravity. This person weighs 686 newtons. And pointing in the other direction, we have the normal force pushing up on the person's feet. And the normal force is what the question asks for. Find N. It's an F equals MA problem. Summation of the forces in the y direction equals M times AY. Well, actually at this particular moment, AY, I could have just called it A. The X component is 0, okay? As the person is approaching the bottom, they'd be gaining speed. After they've passed through the bottom and are going up the other side, they'd be losing speed. But at this particular instant, that's why I put the person right at the bottom of the arc there, because at that particular instant, they are neither gaining nor losing speed. The only component the acceleration would have is in the y direction. At this particular instant, both of the forces are vertical, and some of the forces in the x direction is equal to 0 because there are no forces in the x direction. Let's fill stuff in. I'm going to say up is positive. So positive N. In the negative direction, 686 newtons. Mass is 70 kilograms. And since at this particular instant anyhow, our skateboarder is in uniform circular motion, the acceleration toward the center of the curve, which is somewhere up here directly over this person's head, since they're in uniform circular motion, their acceleration must equal v squared over r. So I said earlier, the way to get the wrong answer is to calculate mv squared over r. Well, I mean, you do have to calculate mv squared over r. The problem is saying that that's equal to the normal force. It's not one individual force that's equal to mv squared over r. Well, it was with the car on the curve because there was only one force acting. The sum of the forces equaled the only force that was there in the one with the car. Here, though, there's a couple of forces. It's their resultant, which equals mv squared over r. So if you just set, if you just calculated mv squared over r and said that's the answer, you'd be off by 686 newtons. So we've got there it is. Couldn't find my piece of chalk. $70 times 100 squared divided by 5, you get 1,400. Add the 686 to both sides. (2,086 newtons). If this was a question on a test, I'd give you full credit for that, because I said, I wasn't really going to penalize you for the rules on significant figures. But if you are going to make an effort to express that as 3 significant figures, see, if you leave it in decimal form and round it off to 2,090, somebody looking at that doesn't know if that 0 is a significant figure or if it's only there to show you where the decimal point belongs. Whereas if you convert to kilonewtons, if you wrote it like that, that clearly has 4 significant figures. Whereas if you do that, that clearly has 3. It removes the ambiguity. So that's the reason I expressed the answer that way instead of this way. But I'd let you get away with that. There are more important issues in this problem than how you round off the answer. Next problem involves turning the page. Yeah, I gotta let it down the rest of the way. Well, if there's anybody out there who likes to know all the physics words for everything, this would be called a conical pendulum. Simple pendulum is a mass on the end of a piece of string. If you just pull it to the side and let it swing back and forth in a plane, then, simple pendulum. But here you pull it off to the side and then give it a push in a direction that's to the side instead of toward the equilibrium point, so that you get the mass going around in a circle instead of just back and forth along an arc. So as it swings along, the string tracing out the surface of a cone, the string is making a 40-degree angle with the vertical. And it gives the mass and the speed and the radius of the circle it's moving along. What is the tension in the string? This is another example where you can get the wrong answer by just simply calculating mv squared over r. Okay, 2.3 times this number squared divided by that radius will not give you the correct answer. Once again, it's an F equals MA problem. Start with the diagram showing the forces. There's the string and the mass on the end of it. You've got the force of gravity pulling down. And you've got string tension pulling in that direction. Our objective is to find T, the string tension. After you've drawn the free body diagram, the next step is components. Nothing to do here, that's straight down. As for the components of the string tension, we've got a little more room to write over there, I guess. The X component is the opposite side, okay? We have here an angle measured from the vertical. So the opposite side is the X component. That would be T times the sine of 40. Or cosine of 50, if you really want to do it that way. The Y component would be T times the cosine of 40, but I'm not going to bother writing that down because it turns out I won't be using it for anything. Some of the forces in the X direction is equal to MA because it's accelerating in the X direction. Same way I started out the one with the skateboarder, same way I started out the one with the car on the curve. The sum of the forces equals MA, and the acceleration will be equal to V squared over R because this thing is in uniform circular motion. The only force in the X direction is the X component, T sine of 40 degrees. Okay, it's the X component that points toward the center of the circle, not the string tension itself. So in this case, if all you did was calculate mv squared over r, you would be off by a factor of the sine of theta. Fill in the numbers. Finish it off. Mass is 2.3 kilograms. We've got 3.21 meters per second, and you square that. So I divided both sides by the sine of 40 to solve it for T, and also filled in all the numbers. Mass, V squared, 1.25 meters for the radius. Get your calculator, push some buttons. .29.5 newtons. There is an alternate approach, which is just as correct and probably just as easy. If you don't like doing it this way, you could say some of the forces in the y direction equals 0, because the acceleration is horizontal. Okay, the acceleration is toward the center of the circle. The ball is not going up or down any, so some of the forces in the y direction is equal to 0. Therefore, T cosine 40 is equal to mg, 2.3 times 9.8, and you can solve for T out of that, and you ought to get the same answer if you do it that way instead. Seven. This is one where we will just calculate mv squared over r, and that's all there is to the answer. But the question is there to give me an excuse to talk about a few things I want to talk about, even though answering the question itself is more straightforward than some of the other ones that I did. So we've got a spaceship. It gives the orbital velocity, a little over 7,000 meters per second. It gives the radius. Now, that is not the altitude above Earth's surface. That is the radius of the orbit measured out from the center of the Earth. Find the force of gravity on this astronaut. So, a couple of ways of doing this wrong. One way of doing that would be to say, trick question, everybody knows there's no gravity in space. Actually, there is. Gravity is what holds these spacecraft in orbit, okay? These pictures of astronauts you see floating around, they're only a few hundred miles. Any sort of, well, aside from the moon missions, any kind of manned mission I've ever heard of is in a pretty low orbit. They're only a few hundred miles above the surface. Earth's gravity is sufficient to hold the moon in orbit. The moon is almost 250,000 miles above us. At an altitude of a few hundred miles, the Earth's gravitational field is not actually a lot weaker. It's somewhat weaker, but not a lot weaker than what I've got in this room here right now. So no, the weight of the astronaut is not truly, yes, the astronaut's apparent weight is 0, but the actual force of gravity on this astronaut, no, not 0. It's also not 75 kilograms times 9.8. There's nothing wrong with weight equals mg. The problem is g is equal to 9.8 at the surface. The higher you go, the weaker gravity gets, and at this altitude, g is something else. So off the top of my head, I don't know what number to stick in for g. I just know it's not 9.8. It would be something less than that. So this leaves me with a couple of things to explain. And the first one is, okay, if there's all this gravity out there, because like I said earlier, if there was no gravity, the spaceship would move away from the Earth along a straight line, okay? If they're staying in orbit, there's gravity keeping them there. So how does the astronaut float around? Well, it's not so much because of a true lack of gravity, rather the astronaut is in free fall. You can actually do the same thing right at the surface of the Earth, although I wouldn't recommend it. But let's say you were in the elevator right over here, and we're kind of riding along in the elevator, holding a pencil in your hand like this. Now, I don't think elevators are actually designed quite this simply, but if you imagine an elevator to be like a little room being pulled upward by a cable, what if the cable broke? So that now the elevator starts to free fall down the shaft. Well, if you're inside the elevator, you might be startled, to say the least, which might make you let go of the pencil. And what happens next? Remember, gravitational acceleration is the same for everything. For elevators, people, pencils, they all accelerate downward at a rate of 9.8 meters per second squared, at least if they're going slowly enough that you can ignore air drag, which means the ceiling is not going to catch up to the pencil. The pencil is not going to catch up to the floor. Since everything is accelerating at the same rate, the pencil is going to just stay right in the middle of the room, which means relative to the elevator car, it's going to just float in the middle until you get to the bottom of the shaft, and that's kind of nasty. But a much safer way to do the same thing is in an airplane, and they in fact started doing this to train astronauts back in the 1960s. Today you can charter a plane and take a ride like this yourself if you want to. There are a number of videos on YouTube. Just go in and in the search box, put the phrase "vomit comet." That's what the astronauts named the airplane back in the 1960s, because apparently in the early days, they didn't have a lot of good anti-nausea drugs the way they do now. There was one that I remember, if you go into the website where I have the homework solutions and everything, there's a link you can follow there that takes you to some new YouTube videos that I thought kind of were relevant to the course. And there's one of those that was shot in a freely falling airplane like this. If you've got nothing better to do, you might go look for that. Or as I said, you can find others easily by searching on YouTube also. But what they do is they get their airplane and they get it going along like that, up nice and high. And then they don't exactly turn the engines off, but they take them down to an idle so there's no thrust. And you let the airplane freely fall for, I don't know, 20 or 30 seconds. And it gets to about there, and the pilot says, yeah, I'd really kind of like to have those engines going again. And so he gets it going, and you get back up in here, and you can cut them out again and do it over again. And on a typical training mission, they would do that 20 or 30 times. And I guess you can see how someone might get a little nauseous this way. You wouldn't want to do this in just any airplane. They take out all the seats, they put padding on the walls. But aside from that, what you'll see during the part of the flight where the airplane is a freely falling room is everybody and everything floats around in there, just like you see in these videos of the International Space Station or old videos of the space shuttle or something like that. And this is at an altitude that many of you have been at yourselves flying in commercial airliners. The difference is the commercial airliner just goes along like that. It's not freely falling. So that's a lot like being in this room. If you take away the thrust from the airplane, from the engine, so that the airplane's freely falling, then yeah, you float around. So-called weightless astronauts are not truly weightless, they're just in free fall, okay? And as you can do that right down here near the surface. The ship drops at the same rate you do, so you float relative to the ship. Okay, so the other thing I should probably explain is, okay, all these satellites, or the moon for that matter, is a freely falling object. Personally, I get sort of a disturbed feeling if I sit in the backyard and look up at the moon and think about this too hard. It's like, that is a really large, heavy object. And in a sense, there isn't anything holding it up. You think about that too, yeah, sometimes it's better not to think about certain things too hard. But so what is it that holds up the moon or any of the many artificial satellites? Or what is it that keeps us from falling, keeps the Earth from falling into the sun? Well, let's say you were playing baseball. There's the ground, and you're standing over here with a bat, and you manage to hit the ball dead horizontal. So it goes flying away in this direction, but I just got done talking about projectiles. What happens next is, even though it was shot horizontally when it first came off the bat, as it moves along, gravity is pulling down on it, so it starts to fall. As it's moving horizontally, it falls faster and faster, and so it follows an arc and hits the ground over here, if nobody catches it first. Now, I have oversimplified just one little thing when I drew this sketch. As you have probably heard, the Earth is not flat. Now, over the course, over the size of a baseball diamond, That doesn't make any difference. But what if you could fire the baseball at a really, really high speed? You'd never do this with a bat, but maybe if you shot it out of some enormous cannon or something like that. I don't think I have it written here anywhere, but if my memory serves me correctly, the speed you want is, I'm pretty sure, I think it's 17,700 miles an hour, something like that anyhow. So if you could shoot the baseball at nearly 18,000 miles an hour like that, what happens next? Well, traveling through the atmosphere at that speed, there'd be so much friction, the ball would get very hot and vaporize. But let's imagine a planet identical to the Earth, except that it has no air. You're playing baseball in your spacesuit, and there aren't any mountains in the way. It's a really perfectly spherical Earth. So if you've shot this thing at nearly 18,000 miles an hour, in the time it takes to fall, however far that is, 4 or 5 feet, at that high speed, in the time it takes to fall 4 feet or so, it's going to have gotten much further downrange than it does in an ordinary baseball game, okay? It's going to be several miles off to the right by the time it gets to here, and that's far enough that the curvature of the Earth matters. So when the ball gets to here, it isn't any closer to the ground than it was when you first fired it. And as time passes, the ball continues to drop and the Earth continues to curve. And I think maybe you can see why after about an hour and a half you should duck, because it would really hurt if you got hit in the back of the head by something going almost 18,000 miles an hour. Now, when I explain it that way, it comes across as kind of a silly little story, but what they do when they launch a satellite is actually not much different from that, okay? The rocket, first of all, lifts the satellite at least a few hundred miles above the Earth and gets it up where there's little, if any, air drag. The rocket also gives it the necessary speed that I was talking about, and then the rocket runs out of fuel, okay? Any of the artificial satellites that we've put up over the years, or for that matter, the moon, does not have thrusters on it that are constantly running, holding it up. You get it high enough, you get it fast enough, and then you jettison the booster, and the satellite just coasts. It's a freely falling object. And the reason it doesn't fall down, even though it's a freely falling object, is because it's moving to the side fast enough while it falls that the Earth curves out from underneath it. The Earth has been falling into the sun for over 4 billion years now, and lucky for us, it just keeps missing. So that's some background information for question number 7. The question itself, as I said, is fairly straightforward. Here's the spacecraft. Give it a little tail fin. There's the astronaut floating around. Astronaut's got kind of a small head. That looks a little better. There's the astronaut floating around inside the spacecraft. There is the only force pulling on the astronaut's weight. That's what the question asked for. Remember the question? That was like 10 minutes ago. The question was, find the force of gravity on this astronaut. Gravity provides the centripetal force. Summation of the forces in the y direction is equal to ma. Every vertical arrow on the picture becomes one of the terms in this summation. There's only one arrow. A is equal to V squared over R. Mass, 75 kilograms. 7068. Yes, I did carefully calculate that I was using the correct speed for this particular altitude. Which actually is higher than the space shuttle or the space station actually operate. So at that altitude, this is about 2/3 of what the astronaut would weigh at the surface. Well, then we come to the matter of centrifugal force. Centrifugal with an F rather than centripetal with a P. Force away from the center, an outward force that you think you experience as you go around a curve. I have heard of physics teachers who like to pound into their students, there is no such thing as centrifugal force. I think I disagree with that. There's something happening. The problem is not one of whether it exists at all. The problem, oh, that's where that went. I was looking for that little spring yesterday and I didn't know what I'd done with it. Just a second, I'm going to pause this and put it someplace where I won't lose it again. Clearly some sort of effect exists. The issue is one of classification. A centrifugal force is not a true force. That's why I've got it in quotation marks. Let's say you're driving along in your car. And once again, we're looking down from above, okay? You're in a convertible and somebody's watching you from a helicopter. And you've been to the store or a roadside stand or someplace where you've bought a carton of eggs, which is sitting on the back seat all the way at the right-hand end of the seat. And perhaps just, well, obviously this is not you, but somebody else who is an overly aggressive driver takes a curve quite a bit faster than would have really been the best idea. And so the eggs get thrown across the car and smashed against the door on the other side. And you're going to have a hard time convincing somebody that has egg goo all over everything that there is no such thing as centrifugal force. Oh, the centrifugal force threw the eggs across the car and they all got smashed. Well, let's simplify the situation a little bit. Realistically, what's going on is that the friction between the seat and the eggs is insufficient to hold the eggs back. But to simplify the discussion, let's just say there isn't any friction at all. So you've got the eggs sitting on this frictionless back seat. And as you go along, the eggs will obey Newton's first law, okay? Each of these little rectangles is supposed to be the car at a later time. First the car is here, and then the car is here, and still later the car is here. In the absence of any force, the eggs follow a straight line at a constant speed. So this straight line that I drew is the path of the eggs, which means that because the car is not following a straight line, I've got the center of the car following this circular arc that I drew. First, the eggs are at one end of the seat, then they're at the middle of the seat, and here they are reaching the other end of the seat where they get smashed. So it's not that there's a force that threw the eggs to one side, rather it's the absence of any force on the eggs. In the absence of any force, the eggs failed to follow the circle. Here. Remember how I said a while ago that if the moon orbiting around the Earth, and if there was a big switch on the side of the Earth and you could turn off its gravitational field, at the instant the force on the moon went away, it would begin to obey Newton's first law, which means it would move away from the Earth along a tangent to its previous path. Notice that this straight line carries it farther and farther from the Earth. That is the nature of the so-called centrifugal force. In the absence of any force, to make something follow a curve, in the absence of a force to hold it near the Earth, an object will get further and further away. So you get what looks like something pulling things outward, when in fact, it's just a failure to pull things inward. So that's the true nature of the so-called centrifugal force. It's an inertia effect. The eggs obey the law of inertia while the car around them does not. You get these types of pseudo forces anytime you watch the world from an accelerated frame of reference. There isn't really any force on the eggs, but you're strapped into this car. You judge everything relative to the car. Relative to the car, it looks like some force grabbed the eggs and threw them outward. Where is this force coming from? You know, a force always has to be due to some object that's exerting the force. I don't know. Well, yeah, it's because there isn't a force. But, you know, you step hard on the gas, it looks like there's a force that throws everything toward the back of the car. You step hard on the brakes, it looks like there's some force that throws everything toward the front of the car. Fictitious forces from looking at things from an accelerating frame of reference. And so that's what this is all about. One more example, and then that'll be the end of section 4. And this one involves centrifugal force. We're going to assume a perfectly spherical Earth, which is not true, of course. But if it was, how much of a difference does the Earth's rotation make in the local value of G between the poles and the equator? You see, if you're standing on the North Pole, around here somewhere. If I'm at the North Pole, right there between my feet is the North Pole. It takes me 24 hours to just go around in a circle like this. That is not exactly going to whip the keys out of my pocket. On the other hand, if I'm on the equator, the Earth has a circumference of about 25,000 miles. I have to cover that in 24 hours as the Earth rotates. A little quick math, that's more than 1,000 miles an hour. So I'm going around in a circle, if I'm in Ecuador, at a pretty good clip. Anytime something is in circular motion, it creates centrifugal forces. So if I'm on the equator, there's a centrifugal force lifting up on me, counteracting the pull of gravity and making me seem somewhat lighter than I really am. Whereas at the North, or for that matter, the South Pole, there is no centrifugal force because I'm not going around in much of a circle at all. And so that lifting effect is absent. So they really ought to take this into account with, you know, like the Olympics and things like that. If you hold the Olympics near the equator, you're going to be able to throw a javelin a little bit further than you could if you held the Olympics in like northern Norway or something like that. Anyhow, so here we have the same person that was previously riding on the skateboard, the refrigerator guy, standing on a bathroom scale, weighing himself. A bathroom scale does not read the true pull of gravity. A bathroom scale reads how hard it's being pushed against. So there are two forces acting on this person. mg, that's the person's true weight. And that will be the same at the equator as it is at the North Pole if you have a spherical Earth, which the question says we're supposed to assume. The weight pulls down, the normal force pushes up. The scale reads the normal force, how hard it's being pushed. You know, if you're standing on a scale, your friend comes up behind you, grabs you around the middle and starts pulling up, the numbers are going to get smaller on the scale because only part of your weight is bearing against the scale, part of it's being supported by your friend. The centrifugal force acts like an invisible friend in that respect. So what's the normal force? Summation of the forces in the y direction is equal to ma. Standing on the Earth, you're not really in equilibrium. I mean, you are to some sort of approximation, but if you take the rotation of the Earth into account, you're actually accelerating a little bit, unless you're standing on one of the poles. It's going to be convenient to say down is positive. That's the direction of your acceleration. You're going around in a circle. You are accelerating toward the center of the circle. So let's set things up so the acceleration is a positive number. So a little easier to avoid getting ourselves into trouble that way. Down positive. So I've got mg in the positive direction. And the normal force up is negative. Acceleration equal to v squared over r. We rewrite this. G true, that's the true acceleration due to gravity on a perfectly spherical Earth. That would be exactly the same everywhere. The scale reads the normal force. Well, let's call what you appear to weigh your effective weight. Well, I didn't feel like writing out the whole word effective. It's long, so I just kind of abbreviated it. But mass times g effective would be your effective weight. Mg true is the actual pull of gravity on you. Once I've done that, your mass drops out. And then rearranging things a little bit, I'll add g effective to both sides, and I'll subtract v squared over r from both sides. Because of the centrifugal force, the apparent value of the gravitational acceleration will be reduced by v squared over r. So at the poles, v is equal to 0, and the effective weight and the true weight are the same thing. At the equator, well, we need numbers to fill in for v squared and r. Speed equals distance over time. I already kind of did this in miles per hour. 25,000 miles to get around the Earth once, 24 hours. But if we're going to do the SI thing, we need meters per second rather than miles per hour. So the circumference of the Earth in meters. Yeah, that one I don't. Well, actually, I do know that one off the top of my head. The circumference of the Earth is almost exactly 40,000 kilometers, kilometers, however you say it. But if you don't happen to have that memorized, what you can look up on your formula sheet is the radius of the Earth. After, in the back part where all the different tables are, like the table of friction coefficients is back there. There's another one. Do I have it right here? Sure, I might as well show it to you. There it is. Page 6. Near the bottom of the page, some physical properties. Mass of the Earth, radius of the Earth, some other stuff like the speed of sound. The source of all wisdom. Physics 1, actually that's not true. There's some wisdom on the Physics 132 formula sheet also. But circumference 2 pi r, and you can get the radius from there, 6.37 10 to the 6 meters So Earth's radius from where I just showed you. As for the time, you go all the way around the circle in 1 day. So you cover this much distance in 1 day, except we want meters per second, not meters per day. This number that I have here is 60 times 60 times 24. Now, footnote, this is actually just a little bit off, okay? By, if I remember right, something in the neighborhood of 4 minutes. To really do it right, what you need here is the length of a sidereal day, not a solar day. And what is the difference, you might ask, if you were here to ask me anything at all? A sidereal day means pick a star. How much time between when that star rises? Well, actually, they would do it by when it crosses the meridian, but let's simplify things. How much time between when that star rises and the next time that star rises? A solar day is how much time between when the sun rises and the next time the sun rises. There's about 4 minutes of difference because as a day goes by, the Earth moves a little bit along its orbit, and now you're looking at the sun at a different angle. Okay, so because I probably shouldn't have even wasted your time with that, the difference between a sidereal day and a solar day is not really part of this course. I just stuck the length of a solar day there. But it doesn't make a lot of difference, 4 minutes out of a whole day. You divide that, multiply and divide, and you get 463 meters per second. That's how fast somebody on the equator is circling around because of the Earth's rotation. So v squared over r, that's the difference. See, the question asks, how much of a difference is there in the apparent gravity between the poles and the equator? At the poles, you get G true. At the equator, it's reduced by this much. So the difference is the v squared over r. Stick the numbers in it. The 463 for the speed. The radius of the Earth once again. .034 meters per second squared. Roughly 1/3%. Somebody who weighs 300 pounds at the North Pole would appear to weigh 299 pounds at the equator, just based on the centrifugal force. Now, another thing centrifugal force does is it makes the Earth bulge at its equator. Centrifugal force not only lifts up on you, it lifts up on every little particle of the Earth itself. It's a more noticeable effect on planets like Jupiter. Jupiter spins fast, okay? First of all, it's a big planet. I mean, its diameter is something like 10 times the size of the Earth. And then on top of that, its rotational period is a little under 10 hours. So you're getting all the way around a big circle in less than half the time the Earth spins. There's a lot of centrifugal force. Jupiter and Saturn, plus the fact that they're basically fluid objects instead of solid, and they bulge quite noticeably. The Earth, not so much, but still, if you're at sea level, you're standing there with the waves kind of washing around your toes at the equator, you are, do I have it written here? Yes, I do have it written here. At the equator, you are 13.4 miles further from the center of the Earth than you are at one of the poles because of the way the Earth bulges. Being farther from the center of the Earth would weaken the true pull of gravity and mean that there's an even bigger difference than just what we've calculated here, okay? So I mentioned when I first started talking about the gravitational acceleration, that the reason I'm just saying 9.8 is you can't go to the next decimal place without getting involved with where you are. The local value of G varies when you get into this next decimal place here. Okay, that is the end of section 4.